Welcome everybody to the Bucky Law. Steve, thanks for getting us started here this evening. And thank you for joining us. Fred, thank you for joining us as well. I know that you're quite early there in London at this time. And Richard, it's good to see you. And thank you for joining us. Why don't we get started really quickly about what is our expectation for the call and what do we hope to take away? And how are you doing? Anne, would you like to get us started?
Okay. I'm very happy to be here on time today. uh, and I'm looking forward to actually to better understanding tensegrity. I just want to put it out there. I think that day we finished the dome, the geodesic dome, and we started on tensegrity. Because we said we had to start it because we cannot stop it there because Richard loves we love that Richard's he really likes the topic of tensegrity, and that we come back to read from, and we read I think into the second page of it, and then we said we'll start again with tensegrity. So I'm not sure if we talked about that. Are we starting with the geodesic dome?
We're starting with the geodesic domes in nature.
Okay, but I'm just putting it out there. I think we finished that section actually. Yeah, but we can read it again, not a problem.
I think that's what we said last Sunday, that we're going to start again from the top of the chapter.
Yeah. Okay, all right, that's fine.
Thanks, Anne.
I'm fine with it, no problem. Yes, Fred, how do you feel, and what would you like to take away today?
Thank you, Anne. I cannot speak too loud, so I hope you guys can hear me. I'm not in my place, and it's 5 o'clock in the morning, and it's really cold. So I'm very glad I made it. I was on time by being early, so this is a cherry on the cake. And the second cherry on the cake is I have my sweet honey tea, so I'm going to be warm very soon. So I'm very delighted to be with you guys on the road. I'm on a very small screen, so it's quite unusual for me. I usually have a big screen, but hey, I'm on time. I'm on the call, and I'm together with you guys. So I'm not in London. I'm in France. So very delighted to be here, and I'm in the shape. I'm still in the shape of the plane seat, so I'm still folded. I'm trying to unfold myself, and that's the shape I'm in, and I hope I can learn a little bit something today. So, Richard, welcome to the call, and how are you feeling today, and what shape are you in, and what is your desired takeaway?
I'm feeling warmer than you are from the looks of it and sounds of it, even though it's still cool here in Calgary. And what shape am I in? I think I'm in still kind of shaky shake shape. I was fascinated, of course, yesterday with all of the re-entry of the lunar explorations and the return to Earth safely, which was something that we all had angst about, I think, in terms of the re-entry issues. But I'm still shaking my head with all of the advances that have been made, all of the technology advantages, and the skill of the astronauts doing what they were doing, and the fact that I think they had high priority this time on taking a photographic record of what they were seeing and experiencing. But I have to admit, with all of that sort of talent, the language matters issue kept coming through from time to time. They were talking about being up there. They were talking about looking down. Even I realized that one of the really critical sort of success points was splashdown. And all of a sudden it hit me, oh my God, here's that word down again. uh, and so I'm still fascinated with the fact that the language doesn't keep up with the actual experience or the advantages. And so I continue to look forward to that kind of learning and a dialogue in this final chapter of fuller explanation. And yeah, so um, Manu, how are you feeling, and what kind of shape are you in today, and what are you expecting out of our dialogue today?
Good morning. I feel good. I'm in a state of equanimity. I'm jumping on the train. I wasn't in last week. I tried to watch recording yesterday, and wow, what I expect is just to catch up and to contribute the best that I can, and then I expect to grow from this meeting to have something that inflates me. I don't know who's left. Is it Joe?
Yep.
Hi, Joe. How do you feel? What do you expect?
No, I'm actually feeling pretty good. Feeling a little better than I have been. Yesterday I finally went to the doctor, and got some medication actually to help clear the infection that I've been dealing with. And I think it's making a difference. But I'm still feeling it. I'm still feeling fatigued from being sick. It's always humbling experience being sick. So yeah, so I'm hopeful that I'm on the mend. I've gotten a little bit of rest. It's been also very busy as far as the final sale of the houses on Wednesday. So that'll be that's a big step. And that'll be closing the book on a chapter of my life. So it'll be it's good. It's exciting to start to see what's next, but it's also some mixed emotions. So in any case, I'm happy to be here today. As far as my expectations here, I'm looking to really kind of finish this book and see and then look back and to see what really needs to be revisited in order to be able to articulate Bucky's thoughts a little bit more clearly for me personally. I'm still dealing with a cough, sorry. And Amy is very good at that. So through this book, I think that it'll be very, very good to look, to kind of look back and see what our final takeaways are. But anyway, as of today, we'll start with the geodesic design in nature. Can everybody see my screen?
What page is it?
For the Kindle version, it's a little different. So I want to say it's 265 for you.
Okay, yes.
It is. That's correct. Would anybody like to read, or I can go ahead and read for us? And I know, Fred, you mentioned that it's a little bit quiet where you are right now. So why don't we I'll get it started. And if anybody would like to read, then we can kind of go from there.
Go ahead.
Geodesic design in nature. Fuller points out that an extremely high frequency geodesic tone polyhedron provides the true model of physical systems, which we interpret as spheres, as, for example, a soap bubble. The notion of a continuous surface equidistant from a central point is scientifically unacceptable. that is inconsistent with physical reality. On some level of resolution, all spheres consist of discrete quanta, untold numbers of energy events interconnected by an even greater number of vector relationships or forces. He has clarified this particular misconception countless times. 535.11, because spherical sensations are produced by polyhedral arrays of interferences, identified as points approximately equidistant from a point at the approximate center, and because the mass attractive or repulsive relationships of all points with all other are most economically shown by chords and not by arcs. The spherical array of points which produces very high frequency omnitriangulated geodesic structures. Our eyes cannot see individual molecules in the delicate transparent soap bubble, nor can we detect the cordial chemical attractions between molecules. Nevertheless, they exist, explains Fuller, and it is our responsibility to understand and teach the truth about the universe. Once again, his goal is to provide tangible models of otherwise invisible phenomena. Of all possible solutions, a high-frequency triangulated shell with icosahedral symmetry provides the most efficient method of enclosing space with a minimum of material and effort. Accordingly, nature relies on this elegant design in many situations, calling for protective enclosures regardless of scale. Examples include small sea creatures called radiolaria, radiolaria. Thank you, Richard. The fibrous web of the eye's cornea, and the protein shell of many viruses. We looked into the structure of spherical viruses in Chapter 8 and can now go into greater detail based on our increased familiarity with geodesic theory. The design problem is familiar by now. Tiny amounts of genetic material must be protected by a tough protein shell. As nature is scrupulously efficient, the choice is clear. A spherical distribution of protein molecules will satisfy the basic criteria in terms of conserving material relative to volume, while icosahedral symmetry will provide the most even distribution. The natural balance sought by chemical forces leads to approximately equal spans, which is geometrically accomplished by high-frequency icosahedral systems. In short, the structure of viruses is a product of nature's eternal tendency toward equilibrium. Geometry imposes the rules. Does anybody have any initial comments or thoughts?
Yeah, thank you. That's a good place to stop. I placed, oh, sorry, Richard. I just have 1 second. I placed a picture that explains what's the difference between a chord and an arc on the in the chat. And I placed a picture of a microscope, electronic microscope, radiolaria virus. Just for illustration. Richard, it's yours.
Thank you for that, Fred.
Yeah, I always get caught up on certain words, and the word that caught my eye on this one is the tendency towards equilibrium. And I'm always looking for kind of an explanation of the equilibrium that he had in mind. And for the most part, it seems to be a question as to whether kind of referring to a static equilibrium or a something that's more robust or oscillating kind of equilibrium. And so it um, it raises the opportunity for a dialogue. So in that sense, I can't say that um, he made a mistake or he was wrong, but I always want to discuss what kind of equilibrium is being referred to when I read the word all by itself.
I have a question to clarify here, right? Because many of you have been in talking about Fuller, and you're very connected with the Fuller community where you are and even around the world. The question is this, because the last time we were talking about things like the cosmic integrity or cosmic accounting has no bankruptcy, and then the world is eternally regenerative, etc. Right? So, are there many discussions out there on how the science, like right now, we're talking about, the fact is to make what is invisible, to make it that we can visually see it, right? So, with that kind of realizations, right? Anybody ever talk about it in, like, do they really look into the economics and the financial side of the industries? Anywhere in any research universities, Bucky Fuller institutes, because it certainly hasn't come here for sure, and the books are really making a mess out of what they're teaching the children in uni. And it's only like if you go to Landmark Forum, Money and You, where there's a lot of Bucky's influence there that you see it. Otherwise, I'm just asking, checking here.
Yeah, there's two people actually. There's one really quickly, and then we'll go to Manu. Is that one gentleman by the name of Mark Buckley? He's actually done a lot of work in this area, and he talks about regenerative economics. And he recently has published a book, and I can share that with his permission with you. John Fullerton is another individual that I could share a video that really goes through how we have incorrectly based a lot of our monetary theory on equations that are not aligned with nature. And he talks about more regenerative approach as well. So yeah, there are people that are discussing it, and not looking at it from a very solely materialistic standpoint, meaning looking at it more holistically than the system and how energy is transferred, as opposed to just looking at it from a monetary theory perspective, which is a lot of it's kind of built on assumptions that are just based off of math within traditional models.
Okay.
Yeah, I have access to both.
Yes, please. I would love to have that. Thank you.
One that comes to my mind right now is the work of Ryan Eisler. And Ryan was first known for her book about the title was Chalice and the Blade, but it had to do with ancient cultures, Minoan cultures, cultures that were matriarch kind of cultures. And she went through several books, and one of her more recent ones had to do with the whole question of economics. And I don't have the title right in front of me, but I would think that her work and leading up to the economic sort of version that she's written about would be of particular interest to your approach to education and what your staff might think about it in terms of incorporating or interweaving into your curricular studies.
Thank you. Actually, the reason why this came up is because this past maybe about less than 3 weeks ago, I realized that the type of parents that we have currently did not understand how much we have done to change out and the education, because the ones who understood us and already saw the outcomes of it when the kids are out there in college, uni, or work, the kids are already mostly graduated out from our school. So the past week, I've been going into classes and checking on that one. And out of it's like less than 10%. In some cases, it's like less than 5% of the children have got siblings who are older and are working and went through our system. So the parents understood us, right? And I'm like, my God, I'm going to have to start all over again to try and get the buy-in from the parents for us to take the kids further, right? So they're still stuck. And maybe a little bit more now. They're beyond the basic rote learning. They want the kids to be happy in class. They want them to pick up more skills. But then I'm going into the real world to hack the education process so that the kids have the high level of mastery before they even finish high school of the real world, right? Whether it's in sciences or business or the creative industry or whatever. And when oh my God, I was like, so that's why I talking about this is just perfect, because not only do I have to, that it'll save me the effort, because if there are already people, experts in the field, talking about how it's going to impact their children economically, if it's not for that, I don't think they will listen. So I'm going to have to go for that and give them some really punchy wake up calls, information to wake them up. Yep. So perfect. Going through this, it just occurred to me that this would be the perfect place to ask. Thank you. I'm complete. Yeah.
Manu.
I will never cease to repeat it. The key to understanding these things is to getting back to basic and principles. You construct nothing without setting principles that are fundamental rule. The first principle here that we've always talked about, we talk about the finite universe, one. We talk about energy flow, always flow to a line of least resistance. We talk about the cosmos being of an IVM structure from inside. So if you take that into account, you notice things that are simple in that at the level of each cube octahedron, you have a balance. And then you have stability. And that stability, as Fred put it, there are two types. Everything is dynamic here. So we always talking about dynamic. It can be stable, equilibrium, stable or unstable. We know that the cube octahedron is an unstable equilibrium. That is, when it reaches that the sum total of all the forces that are interacting onto that point is zero, it changes immediately. It biases. Whereas something like the icosahedron is a stable equilibrium. That is, if you leave it, I mean, the best way to illustrate it is to take a trough and a hill. If you drop a ball a billiard board, for example, in a trough, it goes to the bottom of the trough, it stays there. And the only way to get it there is to energize it in such a way that the kinetic energy of it is going to be more than the potential energy that it has there. If you put that ball on top of a hill, it's just going to roll down. It's never stable. So you can imagine climbing a hill. When you're at top of a hill, if anybody tilts you a little bit like that, you're going to fall one way or the other. So those things together provide the framework for our understanding. All that is said here is that in order to contain anything, you contain it in something that has a boundary. That boundary is something like spherical. But the sphere is a concept. The sphere is a concept. Sometimes I say the sphere does not exist. It is approachable from inside. And the way to approach from inside is to put energy in the system for it to expand. And energy is going to expand in all the 12 directions of a cube octahedron. It's like when you take a soccer ball and you pump it with air, it's going to expand. And that expansion leads you to something. And the best is once, if you're saying that universe is pulsative, that is, it goes to a maximum and come to a minimum. The minimum will be the point at the center of gravity of it. The maximum is going to be something that is cube octahedral. But in between, there is immediate collapse of that. If you decrease, if energy starts folding, it's going to collapse into the icosahedron. And how does it collapse into the icosahedron? The angular difference between the icosahedral and the pentahedron, the pentagon is 12 degrees. And then you need 5 turns of 12 degrees to make 60 degrees. It's just a collapse. Do you understand what I'm saying?
Yes. Thanks.
If you take the icosahedron, the angles are 60 degrees on the plane, for example. If you take the pentagon, the angle is 72 degrees. The difference between 72 and 60 degrees is 12 degrees. In order to form a cycle of integration that is stable, that is a triangle, you need 5 times 12 degrees. 5 times 12 degrees form a pentagon. That's how you, at the level of maximum, that is the next level to the sphere, you can create something stable. Because you needed to change that to brace, how will I call it? This is what I'm trying to say is this guy here. This is an expanded icosahedron. That's the way it's going to be, in the most expanded way. In the most expanded way, it's going to just have one bond at each of the vertices. When is that most expanded? It is the closest to the sphere. And the way it is braced is by a pentagon. By doing it in a way that you get to the equilateral triangles that will cover the whole surface, but at the sublevel of the most expanded spherical one. And that's the way I understand these things. Because when I compare this guy to this guy is obtained from this guy by collapsing these angles. That are by collapsing them like this and folding them in to form, how will I put it? This is a pentagon here, 5 sides. I collapse it like that, and like that. And then it starts forming the 6 relationship that you have per vertex of the icosahedron, the 5, I mean, that you have on the icosahedron. Because if you take the icosahedron, this is one vertex here, the number of faces 1, 2, 3, 4, 5 that you have. Does it make any sense?
It does. I mean, it does. I mean, I think that it also speaks to what we were reading a moment ago. And what you're talking about is essentially what can be seen and what cannot be seen.
Yeah, it's operationally, you are seen from inside. And that's what you remember when we discussed about the boundaries.
Right.
You can build the boundary from inside. From outside, you can't.
Right.
And that's essentially a function of a boundary. A boundary is meant to function, let's just say like a diode in electricity. You let flow in and out in a controlled way. That's the function of a boundary. A boundary is not meant to isolate the stuff. Its boundary is meant to filter.
Right.
What goes in and what comes out. So if you take that analogy, this will be a stable boundary, as you see here. Because you stop here, is like a fence. You stop here on the faces of the equilateral of the icosahedron. You stop the thing in there, and then you let it pass, you let energy pass in or go out through the pentagons. And all of that is stable. Thank you.
Thanks. Right.
Thank you, Manu. I want to add about boundaries that they do not have to be physical in a sense. They do not have to be to materialize in something like you can touch or something like you can physically apprehend. For instance, the boundary of a black hole, you cannot go to the boundary of a black hole and see. There's nothing to see. It is just what's called an event horizon. It's an area which can, depending on the size of the black hole, can be rather thin or rather very large, where time slows to a stop as you get more inside the boundary, and no information can come back out beyond a certain point. But there's no physical barrier there. I mean, there's a physical, but it's not material. It's not matter. It's not a matter barrier. So boundaries do not have to be made of matter. They can just be they can be like an event horizon. That's what I wanted to say. Richard.
Excellent. Just want to say, Fred, you use a keyword, information. That's what it is. It has to do with information.
That's right.
It's more general than energy. I don't know. It is information, as you said.
Yeah. Well, actually, the latest use of words in cosmology is that everything is information. Energy is also information. So that's why I'm using the word information. And regarding to black holes, the event horizon is where, as time slows to a stop, nothing gets in the black hole. Everything goes on the black hole, on the surface. And that's where the theory of the 2D information storage and the 3D or 4D holographic universe comes from. is that all information is in 2D, and the 3D is just a projection, some sort of projection of our 3D world. The world we apprehend is some sort of projection of a 2D informational universe. But let's not go there. It's a little bit beyond the scope of what we're doing. Richard, sorry about that.
No problem. I just was wanting to go back to Anne's sort of original question and her reference to the eternally regenerating universe. And when I think about that sort of context, I'm also thinking about what Fuller was striving to discover, and I think he felt that he made the discovery in terms of what's the function of a human being, why are we here, what are we here for, and where he said, you know, we're the information gatherers and problem solvers to help maintain this eternally generative universe and its integrity. And I just think that particular whole phrase from his work you can parcel out the human functioning part and sort of have a discussion or a dialogue with maybe parents, but of looking at, so what is our function? You know, why are we who we are? Why do we have our kids go to schools that are maybe like Anne's, but maybe like other kind of systems that seem to be failing or not doing as much as they should around the human functioning? And then we get into Fuller's basic sort of invitation is the question around a livenry function or a weaponry function. and he sort of obviously is in favor of a livenry function, or we carry out our human functioning in a livenry way rather than a weaponry way. And somehow or another, a lot of civilization has got itself trapped in the idea of weaponry. And how do I maintain my dominant position in relation to other people? And that, to me, I think, has got to be a fundamental sort of question that's in front of kids in a classroom and perhaps in front of the parents who want their kids to do well and get on well in life and to make contributions in life, to make things better than they were before. So anyway, I was wanting to come back to that particular part of Anne's question around the parents who are having trouble getting what it is that needs to be experienced with or what students need to experience in their educational years and environments.
Yeah,
and then also, you know, I would like to find a way to really connect some of that to Manu's explanations of the energy flow and the stabilization and that sort of thing in terms of the economic kind of question that I think Anne was talking about.
There's a pretty clear link right there, right? I mean, so you know, the idea that there are things that are you're asking the first fundamental questions that students need to be able to answer the question, what does it really mean to live a good life? Right? What's the function? What's the purpose? Why am I doing this in the first place? That's the first question, right? And so one of the things that I would even say that things that also Bucky writes about is the idea of specialization, how that kind of creates a narrow perspective. And, you know, that narrowing of the perspective makes us look like it's more about whatever it is that we do is not looking at the connections between things. And so the economics that don't look at the connections between things. They only look at the more mechanistic perspective, as you've often said. It leaves a lot of things that are unseen. And I think that that directly relates to what Manu was talking about with the icosahedron, is the idea of what is left unseen. So the narrowing of perspectives and the narrowing of thoughts, creates, I guess what Bucky would call the great pirates, the ability to actually then extract things from the, from everyone else, and not make an economy that works for 100% of humanity. It works for a few. So I think that if you're looking at the interconnectedness and how Manu was able to connect that with the icosahedron, and how we're able to actually how the inside and outside are actually related, in the sense that we have to look inside, basically asking ourselves, what does it really mean to live a good life? Or, what's the function or what's the purpose of what I'm doing? And seeing the connections between things, as opposed to allowing the external to push things down on us and make us look at things from a very narrow perspective. So I think that there's a relationship there. But I also think the event horizon actually is very interesting, Fred, and something that Susan, I remember, used to talk about all the time. Maybe bring that up on the Wednesday call. Well, if there are no other comments, then we'll actually maybe go back to the text really quickly. I believe we read that. Reassuringly, observations with the electron microscope of isometric virus shells have consistently revealed icosahedral designs. Dr. Aaron Klug, who first observed the geodesic structure of viruses, wrote to Fuller in 1962, telling him of this discovery. Bucky, delighted by the news, immediately wrote back with the formula for the number of nodes on a shell, 10f squared, plus 2, varying according to 238 and 239 frequency. As confirmation of Klug's hypothesis, Klug answered research and thereby provided Fuller with one of the most valued anecdotes and prime example of nature's economic elegance, which enriched many lectures in subsequent years. Insufficient awareness of spatial constraints causes these natural structural similarities to be perceived as coincidence. As geodesic domes were utilized worldwide 15 years before electron microscopy enabled detection of virus capsids in 1962, the resemblance of the tiny biological forms to large architectural structures seemed to many quite extraordinary and improbable. Science does not, as a rule, take into consideration the active role of space. However, such awareness can assist the prediction of unknown structures based on their functional demands. Another fascinating example was contributed to the inventory of geodesic structuring by scientists at General Dynamics, working on the problem of rocket re-entry, who wrote to Fuller describing their results and enclosing photographs. The experiment involved 2 hemispheres of thin sheet titanium, precisely machined to achieve consistent shell thickness. The diameter of one was exactly 1 inch, 26 millimeters. I'm saying that right. Greater than that of the other. Sorry. So that when The larger was placed over the smaller, a half-inch, 13 millimeter hemispheric cavity separated the two shells. Their bases were sealed together to create a double shell dome, and the air was then pumped out of the intervening space to create vacuum. Atmospheric pressure outside the dome caused its thin titanium sheet to buckle in toward the vacuum. The hemisphere dimpled in a pure icosahedral pattern, as Fuller recalls in a 1975 lecture video. Any comments or questions? If not, I'll keep going then. Like the virus, it had no other choice. The titanium sheet experienced an automatic reaction based on the shape of space. Caving in most efficiently required a symmetrical distribution of dimples. The frequency of this pattern, that is, the number of dimples per icosahedral edge, was found to be inversely proportional to the shell thickness. A thicker shell produced fewer dimples, and vice versa. Considering the above progression, we started with a mathematical puzzle. Geometry laid out the rules and led to a solution. It turned out that nature had been playing the same game all along. That is essentially how Fuller described his experience in developing the geodesic dome. I did not copy nature's structural patterns. I began to explore structure and develop it in pure mathematical principle, out of which the patterns emerged in pure principle and developed themselves in pure principle. I then applied them to practical tests. The reappearance of geodesic structures and scientists' findings at various levels of inquiry confirms the mathematical coordinating system employed by nature. The principles behind the geodesic dome are not new. They are eternal laws of nature. The application of these geometric facts to a building system is new. Fuller is quick to explain. Though similar in patterns, patternings to fly's eyes, geodesic structuring is true invention. Fly's eyes do not provide a human dwelling precedent or man occupable structures. Invention can be defined in the novel Application of Generalized Principles, Chapter 16. We'll explore the concept in more detail. Any thoughts of that when we're talking about patterns and pattern recognition and generalized principles, which are obviously very important? Manu.
Yeah. To me, the most important sentence here was the frequency of this pattern. That is the number of dimples per icosahedral edge was found to be inversely proportional to the shell thickness. A thicker shell produced fewer dimples, and vice versa. Do you understand what it means?
Not totally.
You had the most expanded. You have equilateral triangles that were joined vertex to vertex. And all you are doing here is folding.
Right.
Link thickness to folding. If you are using more wedges, more edges to stack surface against surface, there is going to be less that appears on the shell. Do you get me?
Yes, that I do get.
The whole stuff is finite. If I started with these edges, I don't know how many there are here, but they can be counted, of a certain number. Let's just say I'm just taking 100, like to make the point. And I use 50 to stack these surfaces. This one like this, that one like that. You see here, this stacking that I'm doing here. Have you seen here? I've stacked all of these triangles. There will be less that are going to appear at the surface of a structure that I attain in form of dimples, like the dimples of your face, the wrinkles, because they were finite.
Right.
Some have been used to stack. So that is the energy or whatever that has been used is translated in the thickness. And that's why Fuller say a solid does not exist per se. It is always a construction.
Right.
It's a matter of density of accumulation of things.
Hmm.
So if you look, the thicker the shell produce, fewer dimples and vice versa. And that's all we have. So, and then this is linked to the last sentence that you read. You know, new invention, that is understanding the principles and finding arrangement that espouse the principles, targeting the objective that you are fixed.
Hmm.
Earth stack, let's just say silver in some place. I mine that silver and I use it to do solar panels. How the most efficient can I mine the silver, transport it, use it, and recycle it? That's what it's about.
Yeah, that's clear actually, and that brings together what you were saying before as well, with
Yes.
how energy is then distributed too, and energy can be distributed towards something that is good or towards something that is actually negative.
Yeah.
In a way with what Richard was saying too. And that's a question of whether it's been, if getting back to what Ann was saying, it's something that we're looking at, something that is either regenerative or extractive. So the idea, if you're doing something like solar panels,
Yeah.
leading towards something that's more regenerative,
Yeah.
and that's
And
God, I'm sorry.
yeah. And Joe, that leads me to 2 points that Kelly always used to, and then we don't play them yet enough. And Becky also does it. Kelly introduced, he was always insisting on timing.
Yeah.
Timing. Timing has to do with our actions being in the system. How do we align? Sometimes, it is when are we going to align in a certain way? In our anti-entropic design, that's the second word. Timing and anti-entropic. Okay.
Cool. Any comments or questions? I appreciate that, Manu. It's the more that we have these conversations and the more examples that we have, it starts to make a whole lot more clear. Just thinking about it in terms of energy distribution, as we were talking about a moment ago, but even talking about it in terms of how that relates to comparing the reductionist versus the connection model. You're a mute, Manu.
Really encourage everybody to do this. I can't find it again, but I gave the model how to cut it to Steve. Steve is better at arranging information than I. That was like,
Did you give that to
Steve.
us years ago?
Yeah, years ago. It's about 8 years ago. I
Yeah,
think, yeah.
had to be that long.
So this is a geodesic dome. Build it and know that we are in here. This is what we see. It's also a very, very good example of the boundary we've been talking about. Inside here is our dirty wood that we built in order to get this. And this is just paper. This is typically scissors, a board, paper, and glue. And then you can put like this, all of, you see is here. You see the white and the, how would I call it? I didn't have all the yellow. You see here white. The white triangle here. You see these ones?
Yeah.
There are 12 in total. And there are 10 in total because it's half of the icosahedron here. And they are equilateral. These other triangles that you see here on the pentagon are isosceles. And there is a proportion to it. And that proportion, in actual fact, I don't want to jump, phi. You remember the phi that we talk about?
Yeah, sure.
Yes. But I gave this to Steve. I cannot, for some reason, I've been looking into my document, the ratio of this, of the isosceles to the equilateral, and I don't see. But this angle is 72 degrees. This one. This is 72 degrees. One of the angle is 72 degrees and the other ones are less. It's isosceles. And they link to this equilateral, 60 degrees. And when I was listening to what you were explaining the other day, I think it was Fred, last weekend, that was explaining, that this is what he was talking about. The flattening and the more, yes, and the more energy. You were talking about chords and something else.
We were talking about the diagram. I think it was 13 something.
Yeah, yes. I think it's Fred was explaining. He had that on his screen. He shared his screen, explaining that stuff.
If you look at the
15
at the first drawing I put in the chat, the definition of chord.
Yes.
Can you see it? Okay. If you increase the diameter to as large as you can imagine, as you increase the diameter, the arc is going to flatten.
Mm.
And if you reduce the angle between those 2 points, the chord and the arc are going to come closer and closer to each other until they are undistinguishable. Until the phi, as Manu said, is reduced to a minimum. So that's the idea of flattening.
And that's all we do. We are, I wouldn't say prisoners.
As engineer, as much as we like to bloat our contribution to humanity, all we do is flatten things.
Yeah. That's true. So I think
because we're so hopeless to understand anything that's not flat that we have to flatten it in order to explain it.
That's true.
Yeah. But I think that, and Steve will be happy about this. I'm understanding more and more the idea of locality. The locality is how rich can we, in our environment, do things in a way that is coherent with the laws that are more universal. That's why it has to
That's the
do with,
challenge. That's the challenge
yeah.
right there. Because it's reconciling the local with universal principles. And
The universal principle will always be there. It's there. It's us.
right. But you're talking about coherence.
Mm-hmm.
And coherence requires, that types of like the principles could be there, but they're not being adhered to because that's how contradictions essentially arise and create an incoherence. And so that's why sometimes these behaviors, people end up working against whatever it is that they're working for. And that gets back to even the distribution of energy itself. Let me see. Well, let's try and finish this one section, this chapter, because we're getting close to the end here. So let me minimize that. There we go. Sorry, guys. There we go. So the geodesic domes design variables. The study of the great circle pattern seems at first like a completely abstract endeavor. However, the construction of models demonstrates that spheres with a great number of shorter arc segments have a significant structural advantage over simpler structures and suggests potential applicability. Fuller's early models, based directly on great circle patterns, showed considerable strength, but did not go far enough. A new method of generating geodesic structures was needed to produce higher frequency structures with less variation among chord lengths than the 31 circle pattern. This progression led Fuller to concentrate years of attention on icosahedral geodesic designs. He discovered that the inherently self-stabilizing geodesic polyhedron could be truncated as the basis of a stable dome, figure 15-30. These domes, which could be any fraction of a geodesic sphere, must sit on the ground to complete a system. Depending on the situation, a half sphere truncation, 3/4, 1/8, or any number of other fractions might be desirable. Fuller saw that the possibilities were endless. Geodesic domes could be designed to be built out of almost any material and at any frequency. Figure 13 or 15, 130, 5/8 truncation of 4-vector icosa the basis of geodesic dome. The geodesic pattern is also a variable. In addition to the above checkerboard, Fuller developed a number of other geodesic breakdowns. An icosahedral face can be subdivided by a variety of patterns, each one yielding a different design for potential domes. The most common breakdown subdivides each triangle face with lines parallel to its three edges, as explained above in figure 15-131A. The number of segments along each icosahedral edge specifies the frequency of the resulting geodesic dome, and the number of triangles per icosa face will always be f squared for an f frequency structure. A geodesic dome might be 2 frequency or 32 frequency, depending on the size and material. There's no inherent upper limit, but the exponentially increasing numbers of different strut types become prohibitively complicated at very high frequencies. So that's it. Wait, is that it for that chapter? No. Apparently not. Okay. So I'll just read a little bit further here and then we'll go to a stopping and then we'll just talk about what we've just read, unless anybody has anything they wish to share at this moment in time. The second breakdown subdivides the icosahedral faces into triangles with lines perpendicular to icosahedral edges, producing slightly fewer triangles on the overall structure than the parallel version, 12 per face for a frequency breakdown as compared to 16, and is somewhat less symmetrical. Figure 15-131b, Fuller's diamond pattern is yet another choice. Figure 15-131c. This design is unstable unless constructed out of panels rather than struts. If the situation allows for mass production of panels, the diamond pattern will have an advantage over the first breakdown because of its fewer different types of faces. A number of aluminum domes have been built according to this design. Does anybody do we want to walk through these? I think a little bit more in more detail, since they're actually seemingly maybe walk through this. Maybe I'll read this final paragraph or this next paragraph, and then we can start to kind of break down the patterns, the geodesic pattern possibilities, and as well as the LCD frequencies. Finally, the deliberate omission of certain chords in figure 15-131a produces Fuller's a basket weave design characterized by hexagons, 241 and 242, and pentagons entirely framed by triangles. This pattern lends itself to building domes out of bamboo. For example, struts in a three-way weave are simply tied together at crossings. There are many potential designs. The field is as wide open as the number of ways to symmetrically subdivide icosahedron with great circle chords. The fundamental characteristics of the resulting enclosures are the same. Geometric principles are exploited to gain unprecedented structural efficiency, just as nature, in response to the interplay of physical forces and the constraints of space, produces icosahedral geodesic patterns from many enclosures. Geodesic domes are of virtually unlimited size, can be built by increasing the frequency as needed. The mathematics behind the undertaking is cumbersome, but not conceptually difficult. Calculations are simplified, or at least kept under control by an understanding of symmetry. Complete information from an entire dome of any frequency is contained within its LCD triangle. Using the formula of spherical trigonometry, we can manipulate the central surface angles of spherical triangles to derive values with which to obtain strut lengths. Struts are great circle chords, and each one is subtended by the specific central angle. Figure 131 or 132a. Forgive me. Comments or questions? No initial thoughts.
Where are we stopping?
Why?
Where are we stopping?
We could probably, you know what? Why don't we read the rest up until tensegrity?
Okay. I think we read to that and then we go into comment.
Yeah, I agree. Okay. Depending on the construction methods, depending on construction methods and materials, we might strive to keep struts as close to the same length as possible, or instead try to develop triangles with maximally similar types, or work toward any number of other preferred solutions. Frequency is itself an important variable. Great numbers of shorter struts may be more efficient in terms of supporting loads, but construction is correspondingly more difficult. Such trade-offs must be carefully weighed, and fortunately, trigonometry allows enormous flexibility in terms of potential solutions. Taking advantage of symmetry, we are able to experiment with different strut lengths in the LCD triangle, thereby only manipulating angles and lengths for a very small portion of the whole system while developing the mathematical specifications for an entire geodesic dome. Finally, geodesic domes can be elongated or pear-shaped, or theoretically even shaped like elephants. The constant curvature of a sphere produces the greatest strength. But these other options do exist and can be developed with no more than a pocket calculator and a lot of paper. As a final note, it is important to realize that while the theory behind geodesic domes is strikingly simple and previously contemplated by others before Fuller was granted a U.S. patent to whatever, 2,682,235 in 1954. The actual translation from theory to practice structures involved fantastically intricate mathematical development. As with most invention and design, the initial insight was not enough to produce a 250-foot diameter, 76 meters, clear spanning structure overnight. The subsequent calculations required enormous aptitude and perseverance. Considering the precision necessary to have 6 struts meeting at the same point at thousands of different vertices, minute errors in strut lengths at only a few points will accumulate and produce vast discrepancies elsewhere on the dome, dealing with tolerances similar to that of an aircraft industry rather than a relatively crude building world. Fuller had to develop an absolutely reliable trigonomic data to enable construction of extremely large dome. Trigonometric. Sorry, words there for a moment. All right, questions or comments? I think that was actually pretty interesting on a number of levels, but specifically the idea of precision and the rigor that was actually then required in order to execute on putting these theoretical concepts into production. I gotta be honest, that's how a lot of the data centers that they're constructing today they have a lot of theoretical ideas, but the way that they're actually set up, it has to be with such precision, even the way the information flows and the timing is done, that the slightest bit of the timing being off impacts its ability to develop predictable models, or models that predict accurately, I should say.
I'd like to have more of the story of how that all unfolded when he was commissioned to dome the Ford building atrium, and having never done it, and to meet the kind of precision requirements that we've just read about. It to me, it must be a fantastic story that the calculations that they put together to build that actually worked. And they constructed that dome in a very short period of time. I don't know if there is a more sort of expansive story of how that all came to be and how it worked out that it was as successful as it turned out to be.
How short period of time did they do it?
Hmm?
How quickly did they do that? Do you know?
In a matter of days. I don't recall the exact time, but I think they accomplished it more quickly than they had projected. Brad.
Oh,
Thank you.
okay, Fred.
Yes, I'm trying to get the image recognition of Zoom work, but it doesn't work on my laptop. Seems like my hand raised is not caught up there. We're talking of building a large structure, and we're talking about calculations. Calculations are nothing compared to execution. I've ran factories, and Manu, I see Manu opining there, and he agrees because he's in construction. And he's an engineer, he understands that. Execution is the key. You can say that tolerance is going to be that, but if that tolerance is not that, because your saw is not at the right place and all these things, or some slight disturbance somewhere that cannot be measured at the moment by the quality control you have in place, all these things, or you have a new guy that just put the struts, and then there's a nail that's there or something, and then it's all in execution. This kind of engineering. So calculation, yeah, that's fine. Calculations,
Yeah.
but it's execution. It is
Yeah.
execution. Yeah.
I want to buttress what Fred is saying. It's actually double whammy because you have small, you talk about frequency there and you saw the square of a frequency. That same play in, for example, manufacturing. The different pieces, the small errors increase in square. Secondly, you take those and you go to site. You have to put them together. Mistakes. And all of that accumulate and the structure can crumble. And you will be saying, but I did my calculation right. What happened? You need skill. You need experience for those kind of things. That is in relationship.
Yeah. And you also need the proper machineries and measuring instruments and quality control. That's a whole lot of things can go wrong. Yeah.
Yes. So that is first point. I don't know if we've been talking about frequency, wavelength, and all of these things. Has everybody understood very well what it is? Because it's fundamental for us to understand what we're talking about here and the great circles. Let me share something. Maybe it's superfluous, but you see this construction here. Do you see that?
Yes.
Okay. You see this tetrahedron at the top here is one frequency.
Yeah.
This is two frequencies. And this is three frequency. And you can continue building that. That's what frequency means. Now, the wavelength is inversely proportional to the frequency. Do we know that?
Yeah.
Meaning that the more frequencies you have, the more minute it becomes in terms of the distance between these two things. That is the first thing that I wanted to share with you. The second thing that I wanted to share is that we saw that the
Before you
cube.
explain the second thing, you have to explain again wavelengths and frequency, why they move inverse of each other, because that's very important to understand for everybody. You need to have a drawing for that.
Baby, you help me. Do it. I
You
know that you
need a
can do it
drawing.
very well.
I'm on my laptop. I can't do that here. I'm traveling. I would do it, from home, but I've got nothing here to explain anything.
Okay, let me do it in a certain way.
Let me find yeah, okay, please do it. Let me see if I can find
Yes.
an image on the internet.
Okay. So
But,
I'm gonna do it. I think that I have an idea. You tell me if I'm wrong or if I'm right. Let me take red and green, and then I put on a sheet. I have a fixed distance. I'm just going to draw it, and then I'll show
okay,
you.
I've got something for you. I'll put in the chat, Manu. Then you can use that
Okay.
to explain. And why this you can explain why it moves in opposite direction. See if you can use that.
Let me just show this here. Do you see this thing here?
Maybe
With
we
different
can
colors?
Joe, can you take a screenshot and
Yes,
share
yes.
it?
Oh, sure. Hang on 1 second. Give me
Have
one
you
minute.
taken?
It's very important. It's very important to understand that frequency and the wavelength. They're the same thing, but expressed differently.
Got it. I got it.
Okay. So, can you show it?
Sure. 1 second. Hang
I'm
on.
not as good as Fred, you know. This is the first caveat. My writing is
This
like
is
that of a
I
doctor.
think what you said was very important. You're not as good as Fred.
Okay, oh yes, you can show mine or Fred's thing there. Show both. That's good.
Yeah. You want me to share those with him? Hmm.
Or we can talk on can everybody see the chat box?
Yes.
The key is that from point A to point B, that distance is fixed. We want to travel from here to there. So we are vibrating. We can vibrate slow. We can vibrate a lot. As you see there, you see that what Fred put wavelength. Wavelength is the distance between one peak of an oscillation and the other peak. It's like dividing an interval into many sub-intervals that you put one after the other to cover a distance. And the longer and the length of the interval is the length of the sub-interval is called the wavelength. And do you see it there on the thing? Okay. The frequency is the number of oscillations that you make between A and B, from one end to the other. You see that on the upper side, I have, I don't know, 1, 2, 3, 4, 5, 6, 7. Did I count well? 1, 2, 3, 4, 5, 6, 7, 8. Can somebody count for me? I can't see what. But it's evident that there is more on the top side than on the bottom side, right?
1, 2,
Yeah.
3.
Well, it's another way to graphically design attacking and traversing either tightly or broadly,
Okay.
or
So that
quickly
is,
or slowly.
yes. So the number of those is called frequency. Now, the relationship, you understand that if you have more of the frequencies, you're going to have less of the wavelength or the interval between the two. It's like you're putting sticks between two. I don't know if in arithmetics, in elementary school, you deal with intervals. So the number of those strokes that you have, which is the frequency, the more they get, the less you have of the distance between the two.
Right.
Axis. And the relationship, the precise relationship, is that one is the inverse of the other. The wavelength.
Can you provide me then? All right, so I'm looking at this and I get what you're saying theoretically. Now, can we talk about this and the application of what we were just talking about?
What? You're talking about hertz every day. You know, you say hertz, 60 hertz. What is 60
Right.
hertz?
Right.
Well, one application for me was, in terms of having just mentioned traversing and tacking, is
Sailing.
well, in sailing, yeah, is tacking, and skiing is traversing for me. The solid line through the middle is the fall line, and the high frequency is traversing tightly down the fall line. And the low frequency is the Sunday school or the Sunday afternoon skier or the new skier who is just learning how to traverse the fall line. And so those are two applications of if I'm a new skier and somebody showed me that, they're going to explain that you've got to do the low frequency traversing, otherwise you're going to fall over many times to getting down that hill.
Yeah,
If
and
you're a downhill skier, an Olympic skier, you may traverse that fall line so that it actually visually looks like you're skiing straight down the mountain. But you are traversing in terms of very short wavelengths and high frequency distances or high frequency wavelengths. Yeah.
Yeah. And if you go very fast, you die. Because that would mean going vertical.
Yeah.
That going straight line, you die.
Right.
So you need to wind like that in order to increase your time of travel. Your time of spending the energy that is from the high altitude to the low. That's where you want to go from the high to the low. If you just go straight there, given the energy that is there, you are going to die.
Yeah,
Yes?
when I was learning to mountain ski, I was called a crazy Canuck because I was a new skier, but I behaved as if I was the downhill fast skier. And just like Manu said, everybody thought he's going to kill himself if he keeps trying to go straight down the mountain. Yeah.
Fred is raising his hand there.
Go ahead, Fred.
Yes, I'm both raising my hand and trying to set up my oh, there we go. The image recognition so my hand can be raised up without I have to keep it up. Thank you for explaining, Manu. That is really very, very extremely, absolutely capitally important to understand that. Because when we go down to the structure, nature of universe, this is all there is.
Exactly.
Matter, nothing exists really. All that exists are waves and energy waves. That is all that exists. Anything else is a derivative of energy waves at the below Planck scale level. That's all I wanted to say.
Okay. Now, the other thing that is to add that one is what you call amplitude. We've seen wavelength, amplitude, and period. That's the language. Amplitude is how far do you travel perpendicular to your axis, let's just say in ski, to the axis down, how far do you travel laterally before you turn? That's called amplitude.
Yeah, it's the size and the volume.
In the drawing there, the amplitude would be how high it goes compared
Yeah,
to the
it's the
central
size.
line.
It's both the size and the volume.
Slow amplitude
both.
would be like this, and large amplitude would be like this.
Right. This is AM and
Yeah.
Low
FM.
amplitude.
I mean, essentially. That's
So
what
it's not,
Yes.
this is something that is independent from frequency.
Right.
Yes.
It's
So,
an
so
important-
it is a variable that is at 90 degrees of that of frequency. That's why it is represented like that. So the total energy of this will be a function of amplitude and frequency. It will be proportional to amplitude, but proportional to the square of the frequency. The third thing, yes.
Oh, no, go ahead, Manu. Finish, please. I interrupted.
Yes. Yeah, the third thing that I wanted to bring for us, the 31 great circles. Do you now grasp it easy?
Yeah.
And let me put the way I think that it can be put easy. So we've seen that the cube octahedron fills space. The cube octahedron in space can be subdivided into, you have, the triangles part of it, you have 20 faces and 12 squares. Let's just put it that way. If you take that now, if you take any triangle, it can divide any of those triangles can divide the sphere going through the center by two great circles. Do you see that? If you take any triangle like this, you can cut it. I'm just going to show it here. You can cut it like that, or you can cut it in black. Do you see that?
Yes.
Any triangle can be cut like that by two great circles.
Move it over a little. There we go. I got it.
So you have, in total, in terms of that, you have on one surface like this, you have 10. If you take now, let's just say the pentagons or the rhombuses that you have 12 rhombuses. And every rhombus, let me take a sheet that is clean. Every rhombus that is like this can be cut like that. Do you see this?
Yes.
Any rhombus can be cut with diagonals. So you have 12 rhombuses. You have those. 12 plus 12 plus there were 20. 12 plus 20 is 32. But of those 32, 2 were fixed as referential, as poles. So you take out those 2 from the 32, but you have, once you fix the pole, then you define the the equator. So you add 1. That makes it 31. You get what I have?
Yes.
You have 20 faces. You determine 20 because you have 2, but since it used 2, you divide by 2. So you have 20 faces, you have 20 great circles. You have 12 faces that are rhombuses, you have 12 great circles. 20 plus 12 is 32. But 2 were chosen as referentials to hold your system. So you take out the 2, you have 30. But by so doing, you determine an equator. Because if I fix this across the sphere, it means that I've defined this. I've fixed this one.
Yeah.
So you create an equator. It designates an equator. And that equator has to be added to the number of great circles, 30 that I have to have 31.
It's starting to come together a little bit more clearly now that you're going through that.
Yes. Because this is language that Bucky uses time and time. And it's good that it's grounded into examples that are visual for us
to capture. Yeah, I agree.
yes, to understand properly.
I agree. Richard, you have your hand up, so why don't you go ahead and share and then
One last thing that
Okay.
I gave the last time. Yes. You see the icosahedron, all right? You see the great circle here, physically. You can see where the penta was forming. You see, the great circle of the icosahedron is not a straight thing. Practically. In order to obtain it, you twist it. You zigzag in like this. You see that?
Yeah, I do.
Yes. And what we're talking about is having that and fixing and getting this here. If I fix this one becomes determined. This one here as equator. I fix this as pole. Immediately the equator is determined by zigzagging here. It's very important that you see this. That is not once we bring it to the contracted model, what we're talking about is like that. You see there?
Yeah.
And you can see at a larger level how the pentagon is going to be formed. Because the pentagon, this pentagon that I have here, 1, 2, 3, 4, 5, is formed by the zigzagging, by the folding of the things. This is it. This is a pentagon here. Here. This contour that I'm showing is pentagonal. This is one face, 2, 3, 4, 5. You see that?
Yep. Sure.
And this is not, you see? There it is. You can see the pentagon because as I'm here, I see here an icosahedron. You can see it. If I count the number of faces, 20, I see an icosahedron. This is icosahedron fully. But in order for me to see the invisible, the dual of the pentagon, I need to do this. Okay. If I don't do it like this, you don't see it. No, I need to show it like this.
Yeah.
But if I'm just showing this thing like this, all you're going to see is equilateral triangles.
Let's go to Richard though, because we're getting close to the top of the hour.
Okay, so, cool. Sorry to have taken this.
No, it's important. Yes. It's important stuff to be able to cover. So, but I want to stay try and finish a little bit close to on time anyway. So Richard, why don't you share what you have to say, and then we'll go right into your takeaway.
Yeah, sure. I guess I'm now back to what Manu often talks about, and that's what's the practical application of almost anything that we talk about. And when I was teaching social work, I was really perplexed with one of the kind of factors in our work that said that if a student couldn't maintain a relationship, a helping relationship with somebody, that was grounds for failure. And it often was just a subjective judgment by somebody, a supervisor, somebody that was observing the student and would make a ruling that said, I'm sorry, you're not capable of a good relationship with someone you're trying to help. And I was an academic administrator, and I would get the student who was failed for this to come back to me and basically cry on my shoulder. And so I had to try and find out, why is it so important that this relationship factor was so important that a student could be failed, even though they might be an A student, everything else that they did. And so I actually went back into trying to understand the mechanics of it. And this wavelengths and amplitudes and frequency is another way that helps me explain why it's so important. And I actually use the language of zigzag just almost in the way that Manu was using it, because I was saying that the relationship between the teacher and the student, or the counselor and the person needing help, is a zigzag. It's a back and forthness. It's a frequency wavelength type of movement. And if you get that working in sync, then you actually create motion that is perpendicular to that wavelength. Um, uh, and you get a problem to solution kind of progress. And this is, for me, a very practical way to explain whether it's the relationship between two people trying to move something from A to B, let's say, just like Manu was talking about, or whether it's trying to explain why tacking in sailing is so important, or why traversing in skiing is so important, and also why um, the fishtail movement of a fish in the water, whether it's a goldfish bowl or out in the big sea, it's that fishtail movement that actually creates the motion perpendicular to that axis. And so it really brought me to if you want, a mechanical kind of explanation of something that was a subjective relationship dynamic going on between two or more people. And again, I come back to what Anne is dealing with, because I really think that part of what what she's getting at is this very dynamic, is that how do I get a zigzag relationship going with the parents so that they understand the movement that you're trying to move is of the kind that you're now dealing with. And the same issue is, how do you do something between teacher and student so you get that same kind of dynamic? And it's almost like what Anne was often explained was, is that you can't force a little kid to sit in a chair quietly and take in the teaching from somebody else. You've got to get the dynamic going, and you have to figure out, what kind of wavelengths, what kind of amplitude, what kind of frequency is going to work best between teacher and student, or between teacher and a number of students. And so I would think this is a really good way to try and demonstrate to people about the zigzag that's important in order to get something to move from A to B to C to D. And so I really appreciate this particular session that we're going through, and that's going to be my big takeaway, that I found another way to explain the practical mechanics of a relationship between two or more people to try and move something from A to B. And it comes up back to also my understanding of what I was raising earlier in terms of the function of the human being. And the function is to get that zigzag going back and forth in such a way that you create a livenry movement rather than a weaponry movement.
Mm.
And that's our big challenge as human beings, is how can we make that transition from a weaponry sort of zigzag, which isn't a zigzag, it really is just a weaponry sort of domination. It's sort of forcing others to comply. And you want to get it in this wavelengths amplitude kind of motion. And at some point, we have to figure out a way to have that weaponry zigzag, if you want, jump, jump the fence, so to speak, and get on the other track that is a livenry track. And when we eventually do that, I hope that's something that's going to happen, then we will be carrying out the function of the human being that Fuller thought that's of why we are here on this earth, along with all the other elements and dynamics and working with nature. So thank you for the opportunity to make reference to this practical application, and that's my big takeaway from this reading. So I don't know if I pass it on to somebody else or back to you,
Yes, pass it
Joe,
along.
and
Pass it along.
so I'll pass it along to Anne and your takeaway from this evening.
Thank you so much. I got so much out of today. And already every week there's already a lot, and today even more. And the thing is, we are going in the second round, and I got very different things out of the reading today and the discussions. Yeah. Okay. First, I really have to thank this Fred for pausing the. We could have gone on with the reading and gone on with it, right? But for pausing it to just allow us to just sit on this frequency thing. And I think how it's showing up is very powerful, right? And to even have that foundation for us to even look at how it shows up. And it's just not, because when we look at frequency, we're looking at sound and light and the vibrations and things like this, right? And then today we went down the path of like with the skiing and the relationship part and the fishtail. So wow, no science teachers has ever explained it like that. So thank you very much. The other one is also, and then with between Manu and Fred, the diagrams and the explanation. Thank you. And also Joe and Richard, you sent me the content. Where the starting point for me to get more details, because I know that many people talking about economics differently, but this is like really hitting it very close to what we've been working on, and also our discussions all these years, right? And with Bucky Fuller in the mix as well. So what I did was I just a quick toss into ChatGPT, and not because I'm going to go through the book and the videos, but what it did in a nutshell, it actually talked to me at the end. It says, why this hit so hard for me? Because I've got this prompt. It's a teaching. What do you call it? You teach the AI, right, on your voice and who you are. It says, why this hit so hard for me, especially for your work. It says, given your focus on parenting, human development, values over tools, this connects deeply. It says, Fullerton is saying exactly what you're saying in another domain. So it's not a technology problem, it's a systems and values problem. I was like, wow, this is crazy. I mean, the whole lot of it is pretty strong. And it's asking me if I want to map this directly into the three pillars, the three pillar framework, like what we did with the gaming and the AI when I talked to the parents. Wow, it's like,
Wow.
wow. Thank you so much. Right, and then I'll pass this on to Richard. Richard, what shape are you in, and what is your takeaway today?
Well, I think I just did my takeaway, so
Oh, sorry, I
I'll
need to
skip.
pass. Sorry, I need to pass. Sorry, you pass it to me, right? Sorry, I'll pass it to Fred here. Fred, what's the shape? What shape are you in, and what is your takeaway?
Thank you, Anne. That was an interesting call. And I think I made a mistake on the starting point for today. It was a little bit earlier than I thought, but that was really worth it. That makes and Anne had just an Anne's testimony that it was useful to go again through that because we saw it from a very different angle. Thank you. So maybe that tells us something about what the next book we should read. Maybe we should read that one again. That's that may be something to consider. I know everybody wants to move on and drop that one, but maybe we should read it again. So that's my takeaway today. Manu, how are you feeling today? What's your shape, or what shape are you in, and what is your takeaway? I think you're muted.
I am in the shape of a fox, or I prefer to be in that. Let me explain what I mean.
In the chicken coop?
Let me explain. We have a compatriot here, Clem Sonta. Anybody have ever heard about Clem Sonta? He was a preeminent futurist. He's one of the guys that predicted, it foresaw a few months before the 9/11 attack on the US. And he has this, theory of the hedgehog and the fox. And he has flags. Flag is learn to read your environment. That is, know those principles in such a way that you can see an anomaly, an anomaly, in that environment. That's one thing. If you can read flags and then the approach to things, and that comes with timing. You see, the hedgehog just has one defense. You know what it is, no? When there is any danger, the hedgehog just shows the spikes. It rolls and shows the spikes. But the fox every time eats the hedgehog. If you look at the fox, yes, the fox doesn't go straight into his stuff, into his target. The fox does this all the time. Even playing this in interest. He's not interested. And then at the right time, it will come and then topple the hedgehog. Just push it like this so that the hedgehog is on his back. And then the fleshy part is obvious. Eats it. And that is very potent in life. We are in an environment, local environment, or larger local in universe. Because from Fuller's point of view, universe is very tiny compared to cosmos. So we are in a universe that is finite. And that is fraught for us in terms of our species and others. Is fraught with danger. So we need to be alert and we need to be smart and act smartly, not bluntly, but smartly. And that's the why thinking. or a purpose is important. It is not thinking, philosophizing, it's thinking, I always forget this word, but Becky used it, anticipatorily, and there's another word to say that
Design,
you are, yeah,
anticipatory design.
yes, but to say that you have the end game in mind. You know where you are going to. So that is very important to me. And I think that this call every time is calling me to and then kind of, teasing me to do that, to try to do that. And it's very important. And that's called the game of life. And you want life to be interesting, you got to do what we are doing here. And it's important. So I'm very grateful for that. I took a long time. Who's left? Is it Joe?
Just me. Just me.
Yeah,
No,
Joe.
I appreciate.
What shape are you in, and what do you get? Where do you take away?
Oh, shape of my I mean, I'm in good shape. You know, as I said, just dealing with a little bit of cold here, but I really felt like a lot of the concepts that we're covering, the more we talk about them, the better off we are as far as articulating the ideas. I think the economics part of this is really important for us to understand. I'm leading a series on discussions on economics, different schools of thought, and the philosophical approaches that each one of them take. And I'm going to talk about them in terms of mechanistic type of thinking, uh, and how one thinks of it in much more of a Newtonian sense, uh, versus a regenerative approach. And so I think that is really, I'll share a little bit more about that series once I have it fully together. But it's going to be the history of all these different types of thinkers. And part of it is based off of the positivist movements that have reduced people to and have taken a more reductionist perspective. And these positive movements have been they can improve efficiency but are missing effectiveness. So I think that's that's very important. I think the other part is that going through, Manu, all the things that you shared throughout, going through the idea of higher frequency and thinking about things that are stronger and efficient, but also understanding the AM. I think that this is really getting to a very important concept of understanding happenings themselves and understanding happenings, the observer, and how that fits into the tetrahedron. This is one of those, things that we've been building on the whole time. Is that, what does it really mean to be the observer? It's not just to say the observer, but to actually understand what it means to be the observer. So there's an element of AM and FM that actually factor into that, and what is observed and what is not observed. And that's where the icosahedron is so important to understand. So I very much appreciated those examples, and that you can never talk about that enough. And so those are my takeaways. I think it's going to be fantastic. I did put something in there on the chat. I found it to be very important. And it is based off from the book Range. And it talks about how Freeman Dyson, talked about how we need both focused frogs and visionary birds, and it's profound. I find it. So encourage everybody to take a quick look at that, and if not, If anybody else doesn't have anything to add, I appreciate everybody spending their Saturday night. No, Manu, it's really early there. Fred, very early there. And it's in the afternoon there. And Richard, it's late for both of us. So it's all of us are making an effort to be here.
Yeah.
At the
I'm very time as Fred now. Same time.
Exactly. You and Fred are actually
Yes.
you could
Just
be
exactly same time.
you could be calling each other as your alarms for one another.
Yes.
Yeah, there you go. So now you can WhatsApp each other in order to wake up. All right, everyone. I look forward to seeing everybody Wednesday.
Okay.
Thank you, Joe, for
Thanks, everybody. Thanks, Joe. Thanks, Joe, for
Anytime.
hosting us. Very nice.
Anytime.
Very,
Thank
very
you.
good of you.
Thank you for showing up.